So we're dealing with the second law of thermodynamics, and we introduced last time the property entropy. What symbol do we use for the property entropy? Cap S or lowercase s? What's the difference? One is per unit mass, right? Just like cap H, lowercase h. What are the units on cap S, entropy, SI units? Kilojoules per Kelvin. It's a new property, has some new unique units, and you want to get used to those units. How about that lowercase s? Kilojoules per kilogram Kelvin. All right. We had also an entropy balance statement, did we not? But we only had it for a closed system. And we said that the final entropy of the system compared to the initial entropy of the system, I'll write it in cap S. So it's the entropy change. Sometimes I'll put it like this. The change in the entropy of the system is equal to the final minus the initial. It can go up by what? How can entropy increase in a system, a closed system? It could be transferred into the system. How could entropy be transferred into the system? Only with heat. And so you say, if you bring a small amount of heat transfer, if you divide that heat by the absolute boundary temperature at which it crosses and comes into the system, that's an entropy transfer with it. And so let's sum them up. Let's integrate over the entire process, because the boundary temperature could be changing as I bring in more heat or remove heat. If it's a removal, it's a negative Q. All right. How else? What else is in this entropy balance statement for a closed system? We can have the generation of entropy. Sometimes we'll put 1 to 2 on there saying this is how much entropy is generated during the process from initial state 1 to final state 2, or just leave off the subscripts. So we have transfer in with heat, generation due to friction, due to other sources of irreversibilities. General irreversibilities is a term to describe the generation of entropy. And so that's the entropy change. Let's see. Can the entropy change be positive? Could it be negative? Could it be zero? It can be all three for the entropy change of the system. And a lot of students will say, no, it can't be negative. Well, they're confusing the restriction on entropy generation. Entropy generation, positive, negative, zero. It cannot be destroyed. You can't have a negative entropy generation. There can't be anything better than a frictionless pulley. You know, it's just frictionless is as good as you get. So a lot of students will confuse having the limitation that the second law says that sigma, entropy generation, cannot be less than zero. The best it can be, meaning no friction, is zero. And then if you have irreversibilities, well, often engineers like to reduce the irreversibilities in systems to optimize energy transfer, so they'll strive to make it as small as possible. But that just means there's a bunch of irreversibilities, friction and stuff for entropy generation. But this can be negative. The entropy change can be negative. That just means that property went down during the process. How did it go down? Didn't go down because of destruction of entropy. It went down because of transfer out with heat. Transfer out with heat. Right? Right. Okay. So we just talked about this equation. Make friends with this equation, right? Make this equation your friend. All right. Did we talk a lot about the importance of the temperature entropy diagram in relation to the second law of thermodynamics? We had a lot of discussion about a pressure volume diagram, true? And maybe on a pressure volume diagram you have a process that goes here and then here and then here. So it starts at state 1, goes to state 2, state 3, and it makes this little loop like this going around in that direction, right? So what do you know about, what is the utility of this PV diagram? Well, you think that the boundary work, the integral PdV, I'm going to lowercase v, right? And so this is a lowercase w, meaning it's work per amount of mass that's in the system. Okay. Or if you want cap v and then cap w, that's fine. But you would have that the shaded area is the cyclic work. It's the area enclosed on the PV diagram. And if it's enclosed by expansion at high pressure and compression at lower pressure, it's a positive work. If it's going clockwise, it's a positive work for the cycle. If it's negative, going counterclockwise, then it's not a work-producing device, it's a work-consuming cycle. Okay. Well, you say, what do we have over here? Well, we had that the small change in the entropy is equal to a small amount of heat transfer divided by the temperature. Remember that? That's but it's only for an internally reversible process, int-rev. But here we will write it this way: del Q is equal to T ds. And so if we want to know the amount of heat transferred from 1 to 2, if it's happening along internally reversible process, frictionless process, the type of processes we love to analyze, even though they don't always exist out there theoretically, we try to design systems to make it as close to that as possible, then we can sketch it on a TS diagram. Maybe on a TS diagram the cycle starts here, I don't know, state 1, then it goes up here to state 2, then it goes over here to state 3, and then back here to state 1 again, right? Well, what's the area enclosed by that cycle if you're going this way? Well, it's just like Q, like work of the cycle, this would be Q of the cycle. Make sure this is lowercase s, right? Maybe I should emphasize lowercase s. If you have a cap s, then it's a cap Q of the cycle. It's either per unit mass or not. I'm repeating myself because I want you to remember it. Yes?
You said it was only for reversible processes, but it has to be a closed system as well, right?
Has to be a cycle. That's right. Well, what you're doing is you're putting it together for a cycle, but for each process in the cycle, the area under the curve. So for this one, 1 to 2, I can tell it's that much is the heat transfer into the cycle from 1 to 2. From 2 to 3, this is the area under the curve from 2 to 3, assuming both of those processes are reversible, internally reversible. And then 3 to 1, well, guess what? It's going backwards, isn't it? And so from 3 to 1, it's basically not a Q in, but a Q out. Hence, the area enclosed is the net Q of the cycle. And so there's a great tie-in. When you take a look at a cycle, you do an energy analysis, the work net out of the cycle is equal to the Q net into the cycle. First law. There's a lot of problems that we could analyze. You have a problem where it's not a cycle, it's a process that goes from 1 to 2, and then another leg of the process going from state 2 to 3. From 1 to 2, S is equal to a constant. What does that look like on a temperature entropy diagram? Straight line up and down. What can you tell about the temperature at 1 versus the temperature at 2? What happened? It increased. All right? This is where I'm going to stretch your imagination a little bit, or see if you've started to develop some expertise in thermodynamics by solving a lot of problems and having some insight into the problem. How could that be realized? How could you take a system and somehow not change its entropy, but change its temperature? Compress it. Compress it adiabatically and reversibly. So if you compress it, you're putting work in, energy in. It's going to be realized by an increase in internal energy, increase in temperature. It's going to get hot. And if you did it without any heat transfer, that means no entropy transfer with that heat. So the entropy stays the same. And no irreversibilities, hence no entropy generation. So both of those combined from the second law show it's isentropic, same S. You want to see it in equations? So we would say that with the S2 minus S1 is equal to, let me just write it as Q 1 to 2 divided by T plus sigma 1 to 2. If there's no heat transfer, and if it's reversible, it's isentropic. Big conclusion. But how did I get the temperature to go up? Well, you can put in a lot of work. And there's no entropy transfer with the work. But when you put in the work, the internal energy goes up, temperature's up. How about process 2 to 3? What's happening there? Well, pressure's constant. How can I ever have a process where the pressure's constant? Constant pressure, heating or cooling, that's the common one. And so if the pressure's constant and entropy's increasing, what do you think is happening between here's S2 and there's S3? S3 is greater than S2. It's being heated. So as it's being heated, the entropy is being brought in. Could you have reversible heating? Could you have this term right here be non-zero? Let me rewrite the equation from S3 minus S2 equal to Q. Let me do it this way. The integral del Q over T from 2 to 3 plus how much entropy is generated from 2 to 3. Could I have heat transfer and still be reversible? Yeah, you can. They're two separate concepts. One is reversible, frictionless, think of that, and the other is just heat transfer. You said, but didn't you say if I have a heat transfer through a finite temperature difference that's irreversible? But in the limit, if you let the heat transfer occur with negligible temperature difference, so it's always matched, what you're bringing in heat from an external source into the system is always at the temperature of the system, so that there's no irreversibility due to just pushing it into the system, then it's reversible. The classic example of having an irreversible heat transfer is have a wall, have this temperature 1, this temperature 2, this temperature 1's much, much greater than temperature 2, and you have flow of heat in that direction. And in that wall, if I focus on the system being the wall, there will be entropy generation inside the wall just due to heat flowing through it from a hot boundary to a cooler boundary. It enters at this temperature, it exits at that temperature. And that's why you have heat transfer through finite temperature difference as a source of irreversibility. Well, this problem, let me just encourage you to go back and solve problems like this. I'm not going to spend a lot of time on it, but you would list your states, make a table to organize the information. Engineers love tables. And you say, okay, what properties? Well, I'm probably interested in pressure, temperature, specific volume, internal energy, enthalpy, and entropy. That's the standard list. Have you memorized that or seen it enough? Temperature, pressure, VUHS. And then say, okay, if I know this, and it's water, could I possibly get the rest of these? Sure, the state principle. And then I look and I say, for state 2, all the information given, is there anything that'll help me determine state 2? You look backwards from 3 to 2 because you know, oh, pressure 3 is given, and it's a constant pressure process from 2 to 3, and so you kind of go this way and you say, I can deduce P2. And then what else? Entropy is the same on the process from 1 to 2. From 1 to 2, S1 is equal to S2. So since I was able to calculate S1, now do these two properties fix the state? If they're independent, intensive, sure. And they are for this problem. So knowing pressure and entropy, it may be a challenge in our tables, but you can go in and get the other properties. And now, how about for state 3? Well, it was pressure, and somehow the temperature is given at 400, so you can get those properties. Now, once you have all the properties, you want to be able to determine the heat and transfer and the work transfer for the process. So what is the W 1 to 2 and the Q 1 to 2 for process 1 to 2? Can you kind of tell what that would be? I'm not giving you the numbers, but the method. How would I get what I'm asked to solve for, the heat transfer and the work transfer from 1 to 2? Well, we talked about this, right? For the process 1 to 2. If S1 is equal to S2, looking at the second law, what can you deduce? It's adiabatic. And so, true. From the second law, we determine that. Now, what about the work 1 to 2? You're just always jumping between the first law, second law, second law, and then you just get properties. But really, don't ever forget the first law, second law. So if I write down the second law, it helped me deduce Q1 to 2 is 0. If I write down the first law, it's going to be that the Q1 to 2 in minus the work 1 to 2 out equal to U2 minus U1, the change in internal energy, neglecting changes kinetic potential energy. True? Do you like that for the first law? So what did we just deduce about the heat transfer? And so the work 1 to 2 is negative U2 minus U1. You have the values of the properties that you had to look up. Do you think that work 1 to 2 is going to be 0? Do you think it'll be positive? We just talked about that. We said, hey, you're going to compress it. So it's going to be a negative. Negative, that's exactly right. So a lot of times if you're thinking through it, you say, hold it, I think that should be negative because it's a compression process from 1 to 2. All right, how about now to calculate the work 2 to 3 and the heat transfer 2 to 3? Well, we're going to use first law and second law with all these properties we're able to deduce. What about the work 2 to 3? Integral PdV. Absolutely right. So this is the integral, the pressure change in the specific volume from 2 to 3. That pressure is constant because it's a constant pressure process, and it boils down to just your P, which is P2 or P3, let's call it P2, times V3 minus V2, and you were able to get all the specific volumes, and there you go. That's how you calculate it. What did we use? Did we use first law? Did we use second law? What did we use here to calculate the work 2 to 3? It's really even simpler than that. It's just that we used integral f dx. It's kind of like the basic definition of mechanical work. Oh, it's not f dx when you have gases expanding, it's PdV, but that's basically the definition of mechanical work. Expanding gases, pushing something. So it wasn't even as sophisticated as the first law or the second law. It's just like integral f dx is work, basic definition. All right, what about Q 2 to 3? Q 2 to 3. First law of thermodynamics for the process 2 to 3, right? If you write the first law for the process 2 to 3, you get Q 2 to 3 in minus the work 2 to 3 out equal to the final U3 minus the initial U2 for the process. And we just calculated that one. And we have the properties from our table. Hence, from the first law, we're able to calculate that it's equal to work 2 to 3 plus U3 minus U2. So what did we use? First law. Now, somebody says, why can't we use the second law for one of these? Well, first of all, This integral, let me back up and show you right here on this equation. There's two, this is often very hard to make any calculations of. There's two cases where it makes it really easy, and it's almost like obvious. So what's the first case that makes it very easy to make that calculation? What has to be true about the process? If del Q is always equal to 0. What does that mean? It's adiabatic. Don't forget the obvious, right? It's like, if it's 0, it's 0. It's pretty easy to calculate then. It's nothing. Then the other case, so this was adiabatic. The other case of when it's really easy to calculate is temperature's constant. It's T is equal to a constant. Not T is 0, but temperature is constant. That's called isothermal, because then that T can come outside the integral. Make sense? But the rest of the time, you might be tempted to make this calculation. And there's a problem or two where you can actually do the integral del Q as T is changing, but it's pretty rare. Most of the time you can think of another way to solve the problem and not needing to do that integral, to avoid that integral. But sometimes they give it to you, they say blah, blah, blah. Oh, that integral is equal to 0 because it's adiabatic. Or blah, blah, blah. Oh, that problem's isothermal. I can easily calculate that integral. I think I did this last time. Air is a special fluid, and students will always get this mixed up. Is air treatable as an ideal gas? Almost always. When you see air, it's ideal gas, ideal gas, ideal gas. In rare cases is it so cold or under such a high pressure that it deviates from ideal gas behavior. But what about the specific volume? Is it a function of temperature? Is it a function of pressure? How would you answer looking at this property, this old familiar property? How about this old familiar property of U? How about the old familiar property of H? And the new unfamiliar property S? That's the hard part. That's the emphasis for this whole slide here. So what about the specific volume? Is a specific volume a function of temperature? Sure, right? So you think about ideal gas equation, PV is equal to RT, so T may change, V would be impacted. V is equal to RT over P. Likewise, V is equal to RT over P. Can you see how pressure could impact V? Yeah. How about internal energy? Is it a function of temperature? How about internal energy? Is it a function of pressure? No. And that's hard to explain, and I've explained it about 2 or 3 times this semester, hoping that you get that and retain it. Whose experiment? The name of the individual. Joule. And what type of experiment? Water bath with 2 chambers and a little cock valve in between and a thermometer in the water bath. And a whole sequence of opening it, letting the gas go from one tank to the initially evacuated second tank, and making some observations about the water change, temperature change in the water bath. All right, H. Once you have that U is a function of temperature only, is H a function of temperature? Yeah. Is H a function of pressure? A lot of students will say, well, H is equal to U plus PV, and right there is pressure. It must be a function of pressure for an ideal gas. But PV is equal to RT. And is R or T a function of pressure? No, not really. And so U is a function of temperature only. RT is a function, and so H is a function of temperature only. Enthalpy is not a function of temperature and pressure. It's only a function of temperature. And then S. Well, it's a function of both temperature and pressure for an ideal gas like air. And a lot of students say, get the pattern. U is a function of temperature, H a function of temperature. S is a function of temperature only. That's a common mistake. is a function of temperature and pressure. What would be an equation to get the change in S? Wouldn't it be C sub P natural log T2 over T1 minus natural log of P2 over P1? I left out the R, minus R natural log P2 over P1. Isn't that a good equation for calculating the change in entropy? Yeah? Good. Once we have a good understanding of the second law and the property entropy, we can go back and review something that was very abstract, and it's this concept of a Carnot power cycle. And you can do a Carnot power cycle with air as a working fluid, or as something like refrigerant or steam as a working fluid. But we need to start to remember or describe this Carnot power cycle using the entropy property entropy. So what's the quick review of the Carnot power cycle? We had 4 processes. All of them were internally reversible, no friction. 1 to 2, isothermal expansion. 2 to 3, adiabatic expansion. Notice 2 expansions followed by 2 compressions. Isothermal, adiabatic, toggling like that. Now, what we can do is we want to be able to sketch this on our favorite PV diagram and then on our favorite temperature entropy diagram. If you sketch this process for air trapped as an ideal gas in a Carnot power cycle, you see that there's really only 2 temperatures. There's a high temperature because during the isothermal expansion, temperature's constant. And then from, let's say, from state 2 to 3, you have an adiabatic expansion. The temperature actually jumps or changes from TH to TC. Then it stays at TC, and then it jumps back from 4 to 1, adiabatic compression. So what does a line of constant temperature look like, TH? And a line of constant temperature look like TC on a PV diagram for an ideal gas. True? Then what do we have? Let's go ahead and talk about isothermal expansion at the high temperature from 1 to 2. Here's state 1. Here's state 2. Isothermal expansion. Did I do that right? Now the hard one. 2 to 3. I have adiabatic expansion. Exactly right. To the lower temperature. Then we have isothermal compression. 3 to 4. And then 4 to 1. That's a bad looking 4 to 1, but 4 back to 1, it would be adiabatic compression. What's it look like? The same cycle on a TS diagram.
Can we like picture the PVT with the TSH? Like, are the axes in the same place? Or?
Well, do this. There's only really 2 temperatures, TH and TC. And so one of the processes, temperature is constant at TH. The other process, temperature is constant at TC. True? So now, look at this isothermal expansion for the process from 1 to 2. What is S doing between 1 and 2? Is it staying the same, going up, or going down? It's going up because Q is coming in and bringing with it its entropy, but it's staying TH. Can you see what it looks like on a TS diagram? 1 to 2, constant temperature. And entropy is going up because heat is coming in. You're pretty good. Now let's try the next hard one, which is between 2 and 3. What happens to the temperature? It's going to end up down at TC.
Constant entropy.
But it's constant entropy. Why is it constant entropy? Adiabatic and reversible. No entropy generation, no heat transfer to move entropy in or out. Hence it's isentropic, and you're going to just go like that, down to 3. So 1 to 2, 2 to 3. Well, isothermal compression. Which direction is the Q? Not in, but it's out. It's taking with it some entropy with it out, reducing the entropy. And you're going to stop right where you do the compression, back up. What does the Carnot power cycle look like on a TS diagram? A box, a rectangle. True? Again, we go back and we say, what is the purpose of this PV diagram? And you put the area under each of those curves, gives you an image of the work done during that process. And if you then do the cycle, this shaded area is the work net out of the cycle if it's clockwise. Likewise, what is this shaded area on a temperature entropy diagram?
Energy by heat transfer.
That's right. Energy transfer by heat transfer, Q net for the cycle. If it's clockwise, it's Q net in. If it's counterclockwise, it's not a power cycle. It's a refrigeration or heat pump cycle. And you'll have to put the net Q is out, not into the cycle. So we just did that for the gas power cycle, Carnot gas power cycle. There it is, cleaned up a little bit on both the PV and the TS diagram. Can you do the same for a vapor power cycle? What? Well, think of, get it down first of all on a pressure volume diagram, and you're having this dome. What does that dome represent? Where it's two-phase, liquid vapor. It goes from the top point. What is that top point called? Critical point. All of these states to the right on that line of the dome are saturated liquid, and all of them, what did I say, left or right? I got it wrong on the verbs, but hey. And all of these states to the right are saturated vapor. Now, the hard part is draw two lines of constant temperature on a PV diagram. Well, it's pretty easy inside the dome. It's flat. Isn't that the line of constant temperature? But what does it do? Does it do that? And that's our TH. And let's draw another line of constant temperature. And that's our TL or T cold, TC, lower temperature, cold temperature. So are those two lines of constant temperature on our PV diagram? They look good? Sometimes students say, well, how do you know that? Guess what chapter you need to go back and look at? Chapter 3, when you talk about properties, right? And property diagrams. How else could you remember this? Yeah, focus on the specific volume. What was out in this region out here, what would you call that? Typically it behaves as an IG. What does the initial IG stand for? Ideal gas. And so if it behaves as an ideal gas, maybe you just remember on a PV diagram for an ideal gas, they look like that. They're curved downward for constant temperature, TH and TC. And so doesn't that look like it? Same type of shape. So any which way that you can help try to remember. Now, I need to bring in the heat at a constant temperature. So process 1 to 2. Where's a logical place to start to put state 1? So when I bring in the heat, it's going to bring it in at constant temperature, TH. Well, it's at TH. It's got to be on the red line. Let's bring it in at saturated liquid and take it saturated vapor 1 to 2. Now, what's going to happen? Adiabatic. Let's do the temperature entropy diagram at the same time. Temperature entropy, here is TH, here is TC, You can have a dome, and guess what? Saturated liquid to saturated vapor, there's state 1, there's state 2. Now, where is state 3 on either of these diagrams? Which one's easier to figure out? The state 3 on a TS or a state 3 on a PV diagram? On a TS. TS, state 3 is straight down. Same logic that was applied. Adiabatic, reversible, isentropic. Isentropic, S3 is equal to S2. Now, where is state 3 on PV? Is it over here, straight down, or over there? It's over there. And there's no easy way. It's not a straight line or anything like that. It's just that it does have some expansion. When you have, see this expansion from 2 to 3? It's expansion, and so it's kicking over the volume 2 to 3. Okay, then you come back 3 to 4, and then we're going to do compression. Specific volume is going to change. Here's over to 4. And then straight up back to 1. So it still looks like a box, but it's underneath the dome on a TS diagram. But it's not a box or an easy illustration on a PV diagram. Although the top and the bottom are straight here on a PV diagram if you are going from saturated liquid to saturated vapor. So that's the common vapor power cycle, the Carnot vapor power cycle on both of those diagrams. If you're interested in calculating the thermal efficiency for this cycle, how would you calculate it? Well, you'd calculate the work net out and then Q in. Where is the Q in this cycle? Q, which process? Q in is only Q1 to 2, true? And if you actually go and check some pressures, temperatures, run some numbers, go in and out of the steam tables back and forth, you'll get a number. But if you then stop and compare it to this simple calculation, will you get the same answer? Because didn't we understand that Carnot power cycle has efficiency 1 minus TC over TH? We did. And it's one of these things you almost just have to do it yourself. Pick a problem where you analyze this system in detail using the steam tables and all the entropies and enthalpies or internal energies, and then compute the thermal efficiency. And then do a simple computation, 1 minus TC over TH, and to like 3 or 4 significant digits, it'll match perfectly. And if you had a computer program that had more digits, it'd even match better. It'll work.
Are both of them the actual efficiencies? Like none of them are the efficiency max?
Yeah, that would be the absolute maximum efficiency for that high temperature in and that low temperature out.
For both of them? They're both maxes?
Yeah. If I change and I boost, let's say, the boiler pressure and I change the temperature, well, then the theoretical efficiency went up. The maximum Carnot efficiency went up. But if I just analyze. One other thing is somebody says, well, I don't want to start with saturated liquid and go to saturated vapor. Maybe I want to start at 20% and stop at 80%, and I'll do a power cycle like that. Nobody told me I had to start at saturated liquid and end at saturated vapor. So I want to move state 1 here and 2 there and 3 there and 4 there. And that box here would be like this, 1 to 2 to 3 to 4. It'd be a taller, thinner rectangle in the TS diagram, right? Will they have the same thermal efficiency? They will, because all the heat is brought in at the same temperature, TH, all the heat thrown out at TC, and every process is internally reversible.
Yep.
Pardon?
Is that a corollary?
Yep. One of those corollaries where they say that once you have everything maximally efficient, then regardless of how you might change it, use air as a working fluid, steam as a working fluid, refrigerant working fluid, go from saturated liquid to saturated vapor in the boiler, or 20% to 80% in the boiler, it always is going to have the same efficiency. It's almost too good to be true. It's a startling result. That such a simple equation can have such a profound, widespread application. All right. We did that TS. And there's plenty of problems to be had, isn't there? Let's now review a little bit. Sometimes you'll see the second law described as an increase in entropy principle. So let me just describe that and contrast it with our conservation of energy principle. Energy, one of the things you want to take out of this class is always conserved. You may have forms of energy you want and other forms that are worthless to you, but energy is always conserved. So if I have a system, it undergoes a change in the energy, well, maybe it transferred it with the surroundings, something, but the sum of the change of the energy of the system plus the change in the energy of the rest of the world is equal to 0. Energy is truly conserved. But entropy, the other property, there's an increase in entropy principle. So I have a system. It interacts with the surroundings. During the process, the system's entropy changes and the surroundings' entropy changes. And guess what? It's always greater than or equal to 0. We introduce the entropy generation, sigma, to make it an equality, and that's our statement of the increase in entropy principle. The best you can do is have that sigma is equal to 0 if everything's reversible, but in reality, it's all irreversible. So that's our increase in entropy principle. I did mention about trying to give you some insight into what entropy is as a property. It's a measure of molecular disorder, randomness, chaos, or something. But I avoid the word chaos, just randomness. Well, there's a Boltzmann relation. This is a very simple expression developed many years ago by Boltzmann, where S, the entropy, is equal to K, the Boltzmann constant, there it is, the value of it, times the natural log of W, which is the thermodynamic probability. It's a measure of the random molecular randomness. This equation, we just show it to you. We don't really use it in this class, but it's to help you get a feel for what entropy is. And this is one of those big equations in physics and engineering. Here's some pictures of Ludwig Boltzmann as a young man to an older man. The years that he lived, 1844 to 1906, is an Austrian physicist. This is when in 1905, a guy named Einstein did E equals mc squared, which had a big impact in science and engineering. But basically, this is before Einstein. He died when Einstein was still working in the postal system and working on his theory of relativity. Okay? Even if he published it in 1905, doesn't mean it was widely accepted until many years later. So he's before, even though there's some overlap in the lifetime of Einstein, he's before Einstein. And you can even, via the internet, I didn't take this picture, I didn't travel to Vienna and look at the headstone, but you can find people who will go and take pictures and post it on the internet of people's headstones. And here's his tombstone, Ludwig Boltzmann, and the years he lived, etc. And what's at the very top up there? That's his equation. He worked often hard. He was a contemporary of Clausius. Clausius gave entropy. Clausius then also was doing a lot of stuff in his life, and he got distracted, and he didn't push the envelope on the entropy like Boltzmann did. Boltzmann started to work on understanding it and trying to describe it at a molecular level, and that's where he contributed to it. Clausius was more of an engineer. It's a useful property. I know how to calculate it. Let me do some improvements to the world using it, things like that. Also, he had a lot of other interests, Clausius did. Well, we move from a closed system to an open system. What's the difference? You can have mass transfer across the boundary of the system. Well, we want to write an entropy balance equation for a control volume. So we think about how does the entropy inside that control volume change with time. It can go up if you're accumulating entropy, or it can go down. If it's steady state, 90% of your problems will be steady state, or even 99%. Often that term is zero because it's steady state. But we could have entropy transfer into the system. Maybe right in here you have some Q coming in, rate of heat transfer coming in. It's coming in at that boundary temperature. And maybe over here it's going out. Well, that would be a negative Q dot, not in, it would be out, at a different boundary temperature. So you could have a multiple in and out sides to it, to our control volume. And we have the rate of entropy production inside the control volume. Those terms are familiar. But what's new when you have an open system, you could have mass flow taking with it both energy, first law, and entropy, second law. So it brings in its entropy as well as taking out its entropy. So these are the new things with the control volume. Does that equation make sense? Does it look pretty easy, straightforward? For our control volume, what type of things do we analyze? Nozzle, diffuser, pump, another one, compressor, a what one? Turbine, and heat exchanger, and throttling valve. All of those, first law, right? Now, guess what? Just go back to the same list of devices and second law, until you're kind of tired of it. But that's our class. That's our whole class. That's it. Because once you're able to analyze the components, you put them into a cycle where you have this component with that component and this component, and boom, you have a power plant. Or you have a refrigeration cycle. It's what impacts your life. So we take this very general equation, and if it's steady state, which term is zero? If I have only Q dot in, what does that happen? So it goes to 0 is equal to Q dot in divided by TB. And then I'll still have, what happens if I have only one inlet and one outlet? Let me just write it up here. I'll just have, if I have one inlet and one outlet, it's operating in steady state, it's the same m dot. It's just entropy in minus entropy exit. There's only m dot in is equal to m dot exit. And then we have sigma dot inside the control volume. So even though this equation may look long and complex, often in application it's very simple. Okay? A lot of times I'll write Q dot in, and then maybe I'll put over here, I'll have plus Q dot in, and I'll have minus Q dot out, divided by T out. This would be T boundary in, equal to 0. Something like that. True? Well, you get complex systems and you just analyze them. A system has 4 heat transfers. Well, here's heat transfer 1, heat transfer 2, heat transfer 3, heat transfer 4. What do the dots mean? It's on a rate equation. So it's how many kilojoules per second, or how many kilowatts are being transferred in. So we have 1,000 kilowatts in, 250 kilowatts in, 650 kilowatts, positive out. The arrow makes a difference. See that? And this one is 250 kilowatts out. The direction of the arrow is important. You have two mass transfers. Let's find them. We have steam at 10 kilograms per second, and we have saturated vapor, 10 kilograms per second. And one work transfer, here's our work transfer right here. What else did they tell us? I forgot to emphasize. What are they telling you right here? And right here, and right here, and right there. The boundary temperatures at which those heat transfers occur, which is important for entropy calculations. So the first question, part A, is determine the mechanical power produced. This is W dot out. It's the mechanical power produced. How am I going to calculate W dot? And then do this. I'm going to take a break and walk around. And then you give me the equation. You don't have to run numbers, but give me the equation to calculate the answer for part A, and then give me the equation to calculate the answer for part B, which is the rate of entropy production. Can you do that? I'll see what you get. So let me pick it up here. What we have is first law to get part A, second law for part B. Now, you can write the first law in its general form and then apply it to this control volume. You can do that, but you've done it so many times that you get tired of it. But let's do it this way. What do I have flowing in? Q dot 1 is coming in. I have Q dot 2 coming in, minus a positive Q dot 3, which is out, minus a positive Q dot 4, which is out. So I'm going to put 650 and 250 here, and the negative sign, I'm accounting for that it's out of the system. Then I have a mass flow rate coming in, bringing with its enthalpy in, minus enthalpy out. Are there any other transfers in or out? Sure. I'll have W dot out. So I've kind of written everything as in equal to the flow out. Look good? First law. Now, how about the rate of entropy production? Well, that's a second law. And so here is, maybe I draw it this way. I'll have Q dot 1 in divided by TB1, and that'll be the amount of entropy, of the rate of entropy transfer in. I'll have Q dot 2 divided by TB2, that's an in for the entropy, minus Q dot 3 divided by TB3. Treating both Q dot 3 as positive and TB3 as positive, but I use the negative sign to say it's not really into the system, it's out of the system. Minus Q dot 4 divided by TB4. So those are accounting for the 4 entropy transfers with the heat. We're also bringing in the mass flow rate times the entropy 1, that's an in, minus entropy 2, that's an out. So everything has been the positive ins. You can also put sigma dot as a positive in because it's being produced within the system, within the control volume. And that has to equal to 0 steady state. Does that equation make sense? And now we could solve for sigma dot. It's just throw it on the other side of the equation. I encourage you to solve these type of problems.
Now, would it give us a negative entropy production, or it'll end up positive?
Yeah, I kind of put everything as an in, and this is a positive in. Yeah.
Because entropy production can't be negative, so when you move it over, it won't be negative to result in positive.
Yeah, so I would put sigma dot's equal to negative Q dot 1 over TB1 minus, throwing everything.
The magnitude of the result.
Throw it all to the other side. Mm-hmm.
I mean, the sign.
I'm going to skip that one. I'm going to skip this one, this one. Okay, more problems. Let's move to the next section. This was stupid thing. Just a minute. Well, we have to, we already talked about an isentropic process for a closed system. The entropy initial is equal to the entropy final. That's an isentropic process. Well, we can talk about flow through turbines and compressors and pumps and nozzles. Either the turbine be a steam turbine, hydraulic turbine, or gas turbine, typically gas compressor, and we can analyze the performance of the system compared to if there had been an isentropic process. And hence we talk about isentropic efficiencies for these major engineering components. So let's just jump into it. Let's talk about a gas turbine versus a gas compressor. So here's a turbine. Maybe I just draw it as a box. And it has an inlet 1 and an outlet 2. So what's happening? I have fluid flow through the turbine. What's the purpose of the turbine? To have some power out. And a lot of times, Q dot for the turbine is equal to 0. Isn't that our standard turbine? It's not made for heat transfer. It's made for producing power, shaft power. So we analyze it by introducing a control volume. And we do a first law analysis for the turbine. From the first law, don't ever forget what the first law gives us. The power out of the turbine is equal to the mass flow rate through the turbine times its inlet minus its outlet enthalpy, neglecting changes in kinetic and potential energy. It's adiabatic, steady state. Do you like that? Yeah. What's the second law look like? This was the first law. What's the second law look like? For that control volume, adiabatic, what do we get? Well, maybe I draw it, go 2 steps here. The rate of change of entropy in the control volume with respect to time is equal to Q dot N divided by TBN plus M dot S1 minus S2 plus sigma dot. So, steady state. Is there any heat transfer? Our standard assumption for the turbine is that it's adiabatic. If there is a heat transfer, and there are some problems in this textbook where they want that term to not be 0, then they have to tell you or somehow lead you to be able to make that calculation, and you're going to need the calculator or be given TB. I can just tell you right away. So you could have a turbine that there is some heat transfer with it, but somebody's got to help you decide what TB is, the boundary temperature, so you can make entropy calculations with it. But for this problem, standard assumption, and most turbines you want it to have the standard assumption that it's adiabatic. So we get that the mass flow rate times the change in entropy plus the entropy production is equal to 0. Does that make sense? All right. Let's go ahead and make a sketch of our property diagram of interest. Which property diagram is of interest for the second law? TS diagram. We're going to go from a high pressure inlet P1 to a low pressure P2. That's the way turbines work. I mean, if it's a compressor, the outlet pressure is high. But a turbine, high pressure on the inlet. True? Okay. Draw a line of constant pressure on a TS diagram for gas, ideal gas. What does the line of constant pressure look like on a temperature entropy diagram? I'm gonna pause and walk around. All right, so this is a line, constant pressure on a TS diagram in the ideal gas region. Forget the dome. If you want to tuck the dome in somewhere, put it way down, out of the way. There's the dome, out of the way. No more dome, get it out. Okay, and this is going to be a line of high pressure, P1, line of low pressure, P2. So we're coming in at this point, state 1. Okay? Now, I would like you to help me decide where state 2 should be. Well, I wish I had more time to just give you time to figure all these little steps out, but so it's going to be at P2, and if it's an isentropic expansion through the turbine, if sigma dot, look at this, S2 is equal to S1 plus sigma dot divided by m dot. All I did was rearrange that equation. So if sigma dot divided by m dot, if that's 0, if there are no irreversibilities that are producing entropy in the system, then S2 is equal to S1, isn't it? So on our favorite TS diagram, S2 is straight down. There's state 2. Now, what happens if there are some truly, in true gas turbines, there are some irreversibilities? Where would state 2 go to? Would it shift a little bit to the left or a little bit to the right, or go down further? Where would state 2 go to? Or would it not go down as far? What I want you to do is get that illustration, then say, okay, for reversibles, I know where state 2 is. We're going to call that 2s because it's isentropic expansion from state 1 to state 2s. 2s meaning 2 isentropic from 1. And then 2 actual, or just 2. Where is the actual state 2? Is the actual state 2 kind of in this vicinity, in this vicinity, in this vicinity, in this vicinity? Where is state 2? Actual. You show me, don't call it out. Because I want everybody to do this. Yes, isentropic. Yeah.
So isentropic doesn't.
Okay. Whenever you see in this class, this type of class, isentropic, it basically comes because it's reversible and adiabatic. Now, isentropic only truly means entropy is constant. Couldn't I have some irreversibilities that want to generate some entropy while some heat transfer to cool it to take it away and then still have isentropic? Yeah, theoretically, but there's no problems like that I know of analyzed in this class, in this textbook. Does that make sense? Yeah. So when you see isentropic, it's basically reversible and adiabatic. Does it always have to be that? No. All right, so S2 is always going to be greater than S1. That's why you rewrite the second law this way. And so S2 is always going to be out in that direction. But you're stuck to be on P2, hence, that's where state 2 actual is. So here's 1 to 2 S, and then here's 2 actual, or the book just drops a subscript. I like to put 2A, but the book just puts 2. Now, they will put a solid line indicating what between 1 and 2S. The solid. And they will put a not solid line, a dashed line between 1 and 2 actual. Why do they put a solid line? Because it's an indication that the process is internally reversible along that path. Why do they put a dashed line? Because it is indication that it's not internally reversible. Remember this equation, that Q equal to integral T ds. On a TS diagram, the area under the curve is an indication of the amount of heat transfer. You look at this and you go, hey, I can see the area under the curve. but it's not internally reversible. That's why they put a dashed line. Don't visually interpret the area under that curve as amount of heat transfer. Because under that curve, first of all, it was adiabatic. The only reason S is increased is because it's irreversible. So that's why they use dashed lines. Thankfully, no matter what engineering textbook I pick up, that's been consistently done. Dashed lines indicating irreversible paths, and then processes, and then solid lines are for reversible. Make sense? All right. Well, let's say I want to do a gas compressor. Well, here's my black box. There is this to this, to 1 to 2. What is the difference? Instead of the power coming out, it's going in. Don't I have to supply shaft power to run a compressor? Instead of, well, let's go ahead and redraw the temperature entropy diagram. Let's go from the low pressure P1 to the high pressure P2. Let's start right here. State 1 is the inlet. It's low pressure. Where is state 2 going to be on the TS diagram for the compressor? First find where it's 2S, and then show me where 2 actual is. So the compressor is going to take it from 1 up to 2. That would be 2S. But does this equation still apply? If I rewrite the second law for the compressor, would that equation still apply? Yeah, and so the final exit entropy is greater than the inlet entropy by the amount sigma dot divided by m dot. How much entropy is produced? So will it go this way, or will it go that way to 2 actual? There's 2 actual. Because entropy S2 has to be greater. Yeah. And now, think about this. How about the exit temperature versus 2? This is T2S versus T2. Which one's higher? The actual temperature coming out the compressor's hotter than it has to be, higher temperature than it has to be. Irreversibilities make you put in more work to accomplish the same pressure increase. And it's more work's going to be realized by a higher exit or discharge temperature out of that compressor. Make sense? Okay. Because if I have the gas, if I have constant specific heats, m dot C sub P, this is T1 minus T2. So if the temperature actual T2 exit is higher than T2S for the gas turbine, I didn't get as much work out. And if I come over here, W dot for the compressor, it'll be the mass flow rate, specific heat, T2 minus T1. If it comes out hotter than it has to be, I had to push more in. More heat, I mean more shaft work in. So as a design engineer, what would you like? You would like it to come out for the out of the gas turbine, you would like it to come out as low a temperature as possible, hence a high change in enthalpy, hence a high power out. And for the gas compressor, just the opposite. You would like this T1 to T2 to be as small, that delta T to be as small as possible, hence the change in enthalpy as small as possible, hence the power into the compressor is minimized. Makes sense? Now, what about an efficiency? So we'll use the symbol eta for efficiency, and we'll put it for the turbine. And this will be an isentropic efficiency. Well, what do we want to compare? We want to compare what you achieved, what you divided by the maximum. Actual divided by maximum. What's the thing that we should compare for a gas turbine? it would be the actual work per unit mass flowing through to the isentropic, or the maximum work per unit mass flowing through. What is the actual work per unit mass? That would be the H1 minus H2 versus the isentropic H1 minus H2S. That S on that H2S is important. If you had constant specific heats because it's a gas, you put the C sub P, T1 minus T2 divided by C sub P, T1 minus T2S. Cancel the C sub P's, and there you go.
That's considered maximum because of the reversibility?
Because you would have no irreversibilities, it's isentropic. That's right. How about the efficiency? Let me get rid of this right here. The efficiency for the compressor. Well, it's what you actually have to put in, but isn't that going to be more than the minimum? So instead of actual, you put the minimum over the actual. It's a little different. People get those switched around, right? So it's the minimum work per unit mass. That would be isentropic over the work per unit mass actual, which is your H2S minus H1 divided by H2 minus H1. And if you wanted to put it in terms of temperature, it would be T2S minus T1 divided by T2 minus T1. So you could think of both of these cases. I have a length of a line over here, T1 to T2S. That's the longer length of the line, temperature change. Compare the actual temperature change to the maximum, and I get the efficiency. Over here, we go from T1 up to T2, or T1 up to T2S. Again, a ratio of the temperature differences gives you the isentropic efficiency. Does that look good? Should we press forward? What about a steam turbine? Well, we can almost just analyze it. Let's say we have a steam turbine, it's well insulated, it comes in at 8 megapascal, 400 degrees C. Can you find that point on a temperature entropy diagram? Well, we find it 8 megapascal. Here's 7 megapascal, so 8's a little above it. That's a line of constant pressure. And it's coming in at 400 degrees C. There's 400 degrees C. So right there is state 1. Isn't that state 1? Coming in. And it expands to a pressure of 0.1 megapascal. Well, here's a line of 0.1 megapascal right here. So state 2 has to be somewhere along that line. So let's do the second law first for the steam turbine. We have 1 inlet, 2 outlet. We have the W dot, Q dot equal to 0. Is S2 equal to S1 plus sigma dot divided by M dot? Is that the same equation that we had for the compressor? Or the gas turbine? Same as the compressor too. So where is, this is the S diagram, where is state 2 actual going to be? There's state 2S. State 2 actual could be here, or 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 here. I mean, it's got to be along that line of constant pressure, but increasing S. So maybe it's drawn like that. Maybe that's where it is. So what would be the maximum possible work produced by that turbine in kilojoules per kilogram? They're asking you to calculate W dot divided by M dot max. that's going to be H1 minus H2S, as if it's isentropic expansion, because if I come down here, won't that have the lowest enthalpy? And so you would just calculate H1 minus H2S. Okay, I think you can solve that problem. Sometimes in the steam tables it's a little tricky because you don't know if it stayed two-phase or if it went out in the superheated vapor on the exit. You know, if it stayed two-phase with a pretty high quality or if it went slightly superheated. Sometimes you have to iterate. What happens if they tell you it exits at saturated steam? No, at 120. Actually, this is going to be close to 100. Let's say it exits right there. Let me go back to this problem. It actually, they're giving you information to tell you it actually exits right there. That's where it actually exits. 120 degrees C at the same pressure, 0.1. You can see there's some significant entropy generation. So what would be the isentropic efficiency of that steam turbine? How would you calculate it? H1 minus H2 actual divided by H1 minus H2S. You just have to get the enthalpy at 2 actual as well as the enthalpy at 2S. Okay, so we'll pick up here, right? So we want to do this for an isentropic process, ideal gas. You have variable specific heats. You get that S2 minus S1 is equal to S naught at T2 minus S naught at T1 minus R natural log of P2 over P1. All right. If I look at the tables, that's S naught. It's only a function of the temperature, isn't it? Going down. Why did they put the naught on there? It's at like no change in pressure. If you use that, you have to include that term right there. Okay, for variable specific heats. If it's constant specific heats, it's equal to the C sub P natural log of T2 over T1 minus R natural log of P2 over P1. These are not much different in accuracy. But if you wanted to account for the variable specific heat, there you go. You use it over here. What was the definition of the S naught? Do you remember what that was? Well, we had to integrate the C sub P over T dt from T1 to T2. If the C sub P is constant, it can come outside the integral. You're left with 1 over T dt, that gives you the natural log, and voila, you get that. True? But if C sub P wasn't constant, basically the S naught was the integral from some reference temperature up to the temperature of interest. I need to put it like this. Of C sub P as a function of temperature divided by temperature dt. That's what it is. All right. We spent a lot of time now talking about isentropic process. If it's isentropic, S2 minus S1 is equal to 0, isn't it? Well, come over here and you can do the constant specific heats. If that's equal to 0, S2 minus S1 is equal to 0, then I'm going to have an equation that C sub P natural log of T2 over T1 minus R natural log of P2 over P1 is equal to 0. That makes sense? Well, you can do some algebra. How about we do this? Put C sub P natural log of T2 over T1 equal to R natural log of P2 over P1. In the interest of space, could I maybe push and put the C sub P here? Could I then push them to be the natural log of T2 over T1 equal to the natural log of P2 over P1 to the power, I'm going to draw it like this, R over C sub P? Do you remember that rule about natural logs? Then I can exponentiate both sides. If you exponentiate both sides, you pick up T2 over T1 is equal to P2 over P1 to the R over C sub P. Do you remember these? Did you see these equations in the textbook as you're reading through? Okay. Not only can you do it where temperature and pressure are related, you can get it where temperature and volume are related, or that pressure and volume are related. But they're just mathematical manipulations of the same concept. Oh, for an ideal gas, constant specific heat, isentropic process, boom, these how these properties are related. Okay. You can do the same thing over here for the variable specific heat. If you do it for variable specific heat, you have that this is equal to 0, so you have S naught at T2 minus S naught at T1 minus R natural log of P2 over P1. All right, do it this way. So we have the equation where it's equal to 0. Separate and put S naught at T2 minus S naught at T1 equal to the natural log of P2 over P1. Does that look good? Oops, I left the R out. Divide by R. There, now that looks a little better, doesn't it? All right, so if you exponentiate both sides, you'll pick up that P2 over P1 is equal to e to the S naught of T2 divided by R minus that which you can turn into e to the S naught of T1 divided by R. And somebody made the observation that, oh, we have pressure 2 divided by pressure 1. That's equal to, and we're going to call this PR of T2, some function of T2 only, divided by some function of T1 only. And that function will, we can't call it P, but it looks like a ratio of P's. We'll call it P sub R. This is another case in thermodynamics where I wish they would have just given the name of that new function to somebody in their honor. Right? Call it the something function. Whoever did it first in thermodynamics, whoever came up with it. I don't think it was Gibbs, and I don't think it was Clausius. It was somebody else. Keenan, maybe. Somebody. So I wish they would say, oh, this is the Keenan function, because you can look in your thermodynamics textbook and say, oh, you have a new function, P subscript R. That looks a lot like P cap R, doesn't it? What was the name of P cap R and what was defined as? It was P over P critical. It was the reduced pressure. We used that in the compressibility factor calculation. But this is not the same. P lowercase r is not the same as P cap R. And P lowercase r isn't defined. It's just that P lowercase r is related to e to the S naught T divided by R, and it's a function of temperature only. But students love this for some odd reason, because that's what this P sub R is right there. It's only used when you have an isentropic process for something like air, ideal gas. They only tabulate P sub R for air. It's not in any other ideal gas tables for any other carbon dioxide or carbon monoxide. And here are some numbers. How do you use it? Well, it's only a function of temperature, and you can look up this piece of R as a function of temperature, and then you can more quickly calculate isentropic relations, or to calculate the final state given isentropic expansion. So what they have is they have P2 divided by P1 is equal to PR at T2 divided by PR at T1. And you'll see this relationship here. Likewise, with a little bit of work, you also get an understanding of this V sub R. So V sub R, assuming isentropic process state 2 divided by V sub R isentropic process state 1 is equal to the actual specific volume ratio V2 over V1. All right. I wanted to see if I can use that in a problem. Here's a problem. We'll solve it two ways. We'll use the tables with the piece of R's, accounting for variable specific heats, and then we'll just use it with constant specific heats. Air enters a nozzle. So here's our nozzle. It enters at a pressure 1 of 150 kilopascal and temperature 1 of 400 Kelvin and the velocity 1 of 25 meters per second, and it exits at a pressure 2 of 100 kilopascal. Do they tell me the exit temperature? No. Do they tell me the exit speed? No. But what do they ask? Determine the maximum exit airspeed. So you do a little control volume around the nozzle. You have inlet state 1, outlet state 2, and you do the first law. And then you do the same control volume, do the second law. Can you get the first law for that? I don't have enough time to stop, but I wish I did. Can you get the first law? What would it be? You'd have that inlet enthalpy plus the inlet kinetic energy is equal to the exit enthalpy plus the exit kinetic energy. True? No work, no heat transfer, boom. So if I'm interested in the exit speed, it's the inlet speed squared plus 2 times h1 minus h2 square root. Did I do the math right? Yeah. Now, let's talk about the second law. You're going to have that the no heat transfer. You're going to have that the exit entropy is equal to the inlet entropy plus how much is generated per how much is flowing through. We had no heat transfer. There's no entropy transfer if it's adiabatic. So what about if I wanted to calculate the maximum air speed? Maybe I should, if I assume constant specific heats, I get V1 squared plus 2 C sub P T1 minus T2. If I want a maximum exit speed, what should happen to the exit temperature? Make it as low as possible. True? So if you want it as low as possible, would you want it to have a bunch of irreversibilities in the nozzle? Or would you want the nozzle to be reversible? Reversible. You would want no friction in the expansion. If you go and take a look at the temperature entropy diagram, here's lines of constant pressure, right? And we're trying to go from a high pressure to a low pressure. Let's get rid of that extra line of pressure. If we go like this, didn't I get it as cold as possible? But if there were some irreversibilities, the exit temperature creeps up. And it's not going to come out as fast as possible. So if I want to calculate the maximum airspeed, when you see the maximum, you think of, oh, I need to use the second law. I have to have no irreversibilities. So we have that S2 is equal to S1 for the maximum. Well, if it's S2 is equal to S1, it's isentropic. So let's solve this problem using the air tables that we just solved. We would say, oh, this is the air table. I'm going to use this piece of R concept, no name for that variable, but for isentropic expansion. So we look at it and we say, what is P sub R at state 1? Well, it was inlet temperature of 400 Kelvin, wasn't it? You know what? Did I copy enough? No, didn't copy enough to get 400. Stopped. I got 450 but over here, so I would have to look up and get that P sub R1, which is P sub R at 400 Kelvin. And then we know that the ratio, how you use that, is that you have that P sub R2 is equal to P sub R1 times P2 over P1. Okay, did you look it up for me? Can you read off that number at 400 for P sub R?
3.806.
3.806. Okay, we had a final exit pressure of 100 kilopascal. We have an inlet pressure of 150 kilopascal. So somebody go ahead and run this number. You get that's 2.5373. Okay, now you go back to the air tables and you say, where do I find P sub R2 in the air table? And you'll probably have to interpolate. Okay, so the temperature is between 350 and 360. Is that what you said? And then this is the P sub R. What was the P sub R at 350? 2.379. And at 360?
2.626.
And then so what we have is we have to take this number and we interpolate to get that exit temperature. But if you really need is the enthalpies, interpolate to get that exit enthalpy H2. Once you have H2, stick it in right there and you can calculate V2 maximum. Isn't this interesting? It's like, wow, second law restricts the maximum speed out of that nozzle. All right. If you do it with constant specific heats, I calculated that the temperature exit was 357 Kelvin, and that the exit speed V2 was 298 meters per second. All right. Thank you very much for your attention. Study, study, study. This is a tough chapter.